Happy Monday.
Happy Monday.
Okay. I'm going to share my screen and all right. I guess a few things. You guys have been troopers, getting through a lot of little funk factors, getting things working. I'm gonna suggest that everybody move over to the Taylor server and work on your labs there. I worked on over the weekend. Brad helped me out getting all the packages, including like the Maxent and Java package, installed on taylor.brand.ucsb.edu. So if you haven't accessed that before and you're not in the meds program, then I think just go ahead and send me a note. I think I saw most people in there, but and we'll make sure that you can log in. I have a little bit more of instruction on that in a slide.
Should I send you an email for that or via Slack or what's best?
Yeah. An email is good, and then I'll forward it on to the Brand Compute
Okay.
to ask for your UCSB ID to be granted access to it. Yeah. And feel free to go ahead and do that. This lecture, and then when we switch over into lab, then I'll send those out, and and I can show you what it looks like in a minute here too. And you should notice that the videos are now posted on. I'm posting them on YouTube, so you can go back and watch those. They're just the little YouTube icons. The readings you have to access via your UCSB login because it's behind a UCSB only Google Drive. And so today we're going to talk about decision trees. And let's go ahead and get started with that, and then I'll get into some more announcements. Based on the doodle poll, it looks like 11 a.m. to noon was actually the winner. And so I will go ahead and send a Google Calendar invite with my personal link in it so that you have it on your calendar and you can just click on that link and then you'll get added to a waiting room. I'm avoiding putting anything in a public location with a Zoom link so we don't get Zoom bombed. But hopefully that works well for you. And then it's always fascinating to me that I think that, we're using fairly straightforward R packages, but of course there's something like Java, and it's like there's various installation issues between host machines in different versions that you may or may not have installed and up to date. And whether it's Windows or Mac or Linux, and I mean, like the new M1 processor didn't work with the Java typical install. Anyway, so to avoid all this pain, and when you do have a problem, rather than us having to synchronously, meaning both at the same time, you show me your computer and then Julian pointed out how this is just awesome to be able to access Taylor, because now as an admin, I can actually resume your session and see the exact error message and then look at the files and actually even log in, run a session as you as a user. So it's an identical environment that I can access is whenever I have free time to do so. So that's why you definitely want to move in this direction. So you guys don't have to wait so long to get help. And sometimes the messages are really, it's hard to decrypt without actually getting in there and inspecting. So the easiest way to do this, it would just be to zip up your files and then upload them once you log in. So when you upload in Taylor a zip, it'll automatically expand it to the target destination. So it'll unzip it to location. Or even better is if you have your stuff in a GitHub repo and you're versioning things. And if you do that, then I could also come in and commit a different version and even associate with an issue. And so if you're comfortable setting up this class in your own user GitHub workspace, I would recommend doing that. And then to connect to Taylor, you do have to be on the UCSB VPN. And if you're not, then this URL shows up as not found. So if you're not on the VPN, so you need to install this software on your machine, Pulse Secure, and then have to do a security on your phone probably. And then that will let you in. So yeah, let's just take a quick look at this on Taylor. And this is quite cool. I guess you guys, most of you have used this already in other classes. But it's also interesting just to see how I can, as an admin, so you wouldn't be able to see this, but as an admin, this is what I love. I can look at users, and then I can look at sessions, and I can look at users, and then I can where is it? I can log in as user. So then I log in and I see your stuff, which is great. Now, the other thing is, here's my little session, and here's my home folder. There is on Taylor. So normally, by default, you're just gonna be in your home directory, and the tilde is an indicator of your home directory. So I can change directory. No argument, just defaults to my home directory. I can explicitly say go to my home directory. And then I can also say what is my present working directory. So these are born again shell or bash commands that work in Mac or Linux. And this gives me the full path. So it's under users bbash. So I can look at list all the users, and these are all the user folders. And then I can also change directory to the root and look at what we have here. And we have these courses. So cd courses, and then here's EDS 232. And what you can do is you can add a little symbolic link in your home directory so that you have easy access to this. So I'm going to add this command to the slide. So if you're in your home directory, so cd, I'll just say tilde to be explicit. And then the command is to link symbolically in courses. And notice how also, this is awesome, I can hit tab and it will auto-complete. Because courses is unique, it will complete that path name. And then I can type in the rest of it too, and see now 232 is not unique. There's other EDS 2s. Now, if I do double tap, it'll show me what all the options are. And then, whoops. And then I can give it a name. Oh, well, but it already exists. So that's why it's not doing it for me. But this would be the command that you can run from terminal to add a symbolic link to give you instant access. It's just like a shortcut. So I'll just add that. And to yeah. So all that is right now is it's the GitHub. So I ran a Git clone of actually, I think you can see it in my history. Yeah, here I ran a Git clone, and that's what this is, and the ML. And then this is just a little helper to install the packages. We don't have the packages installed yet on the server for today. This could take up to 5 minutes. So, and it's meaning that it's going to install on your in your home lives. So the way that R installs things, if I look at, I think it's called live paths. So live paths, and I think actually, you can use my folder where I've already installed it. So this is where R looks for packages in my user directory. So if we add this to the beginning of the lab, then I think it might not prompt you for those packages once we get going. So I'll just see if this, we'll have to have somebody else run this to see if this actually works, but if you're logged in, you could give that a shot. And so this is there's a system level library that I do not have privileges to install on. And then there's the user level directory. And that's where if it doesn't find it in either one, it's going to install it here if you don't have permissions here. So this is supposedly going to then add this path. And since I already installed these, you should be able to move on from there. So maybe I'll add this because this is also a little thing, temporary thing. Okay. I think that's it for announcements. So now let's talk a little bit about these different modeling techniques. And we're introducing a new type of modeling technique today with decision trees. So last time we looked at logistic regression, and we specifically with the generalized linear model and generalized additive model. And we saw that we were able to have a more sort of nuanced or wiggly relationship between predictor and response with the GAM, and then even more so with the maxent. And so we're looking at two different axes, and maybe a linear model is a little simpler and there's more wiggles with the GAM. And this use of having a binary response, meaning like it's either we're trying to predict presence or absence. It's a unique case where we were using a regression technique, and regression techniques are actually most useful for having the response term be continuous. So like some number that you're trying to estimate, like maybe the density of the animals or the number of occurrences you might encounter on a given pixel. But because we applied this logit transformation, remember, to make it continuous and constrain it, clamp it down between 0 and 1, we're able to use that regression technique successfully. So that's kind of a unique instance of how a response term can both be where we can use kind of like continuous kind of modeling techniques, as well as a classification technique. So now today we're going to, rather than treat that as a continuous response, we're actually going to treat it as a categorical response. And when I say categorical in R speak, that's a factor. So it's a discrete value. A 0 is totally different than a 1. Present is totally different than absence. Water is totally different than forest, than urban, than, different land cover types. So that's a different category. And that's where classification is generally speaking, referring to different responses. Now, the reality is that you can take continuous response, and then you can create ordinal classes along it and use some classification techniques. So it's not strictly exclusive, but it's generally associated with these different types of responses. The regression tends to use more for continuous response, and classification is generally for a categorical response. So today we're actually going to treat presence and absence as a category. And last time, remember, we had this framework of we take the data in, we're training the data, we're using the training data. We hadn't split it out last time, but we're going to do that today. And we're going to feed the data into a model to fit the model. And then once we have that model object, then we can predict on either the old data, the existing data we trained on, or some new data, like maybe the entire landscape or seascape. And you'll notice that in the case of prediction, it's predict all at each time. We're using the same function. It based on the class of the object that it gets in, it's going to actually, under the hood, use the appropriate packages predict functionality, but it's kind of generic in that sense that we're just predicting using the predict function. Now, the fit function is specific to that modeling technique, and we're using these different packages to do it, and to get the generalized linear and additive and maxent models. And there's other different parameters that we could have also input when we did that fitting. And now we're going to talk about decision trees. So this is a very different animal as far as how the machinery works. We're not using the typical ordinary least squares regression, and then also how the diagnostics look and kind of how it's fitting the model. And what it's doing is it's partitioning the data so that in the end, you get these nodes at the end of this branching graph that tells you like, well, if this variable is this less than or greater than that variable, then this value as some cutoff, then it's going to say branch out, and it's like a dichotomous key to then indicate, okay, if all these conditions are met, then I'm predicting a 0 of absence, or all these other conditions are met, I'm predicting 1 of presence. And so this is a link to the Wikipedia entry. And there are, originally, it was developed by this guy, Bremen, I think he was at Stanford, and it was called classification and regression tree. So meaning that it's actually, you can have a continuous response that it discretizes into these classes of values, but that was called CART, and that's a registered trademark. So we're using RPart, and it's recursive partitioning is this, it's the same idea. And now you can imagine that you could actually have an ensemble approach, and we'll get into that more next time, but a random forest is a tree of trees. So there's actually multiple models, and then it borrows from the different model fits. So these are the two modeling techniques you guys are going to run today. One is this recursive partitioning to fit the model, and then the other one is using this ranger, I guess like a forest ranger, because it's a random forest. Yeah, and then it's similar with the predict step, which we'll get into more next time, actually, with model evaluation and performance. So this is just a little animated GIF where you can see, here's the data on like some predictor X and then some response Y. And actually, I would say this is better thought of as two predictors, X and Y. And the response is the green leaf, either like the tree is present, or a gray leaf, the tree is not present. And what it's doing is you see that the first branch, the first dichotomous key is saying it's picking a split value of 0.5. And you see that if it is greater than 0.5, you see in that tree on the left that it's then allocating to that right half of that quadrant. And then it can branch it again within that space. And if Y is greater than 0.5, it's going to split the top half of that left quadrant and the bottom half of that left quadrant. And then it can branch again and get that lower left quadrant to split. And so that's the recursive partitioning. And you'll notice that also as it's partitioning, it's explaining the most deviance with each partition. So the highest level partition is going to explain the differences the most. And then as it gets recursively within those boxes, it's going to be build out a bigger and bigger decision tree with a difference in the depth of the tree. So that's the important point, so that it's differentiating at the most, it's explaining the most variance at the highest level of the branch, and then it gets more and more detailed as it goes down. So you can see that response. And if you plot it out, then like here's another example, and you can go to this link to see actually the R code to generate these figures. And this split you could also visualize in like a 3D way, where Y is the response, and then these are the different levels. And then there's a great book that actually I only recently encountered called Hands-on Machine Learning with R. And depending on how you learn, this actually it's got a lot of explanatory text and does a much deeper dive in each of these techniques. So I recommend that for more explanation. There's a lot of different bells and whistles and knobs to tweak on any one of these techniques. So we're not gonna, you're not gonna become an expert in any of them, but we will, you'll at least get to use them. Oh, sorry, I wasn't looking at the chat yet. Okay, yeah, let me get to these questions that you guys were asking in the chat. Apologies for not seeing that sooner. Should each lab section for lab 1 be its own RMD, or should we do them all on one RMD? It would be easier for me to grade all on one RMD. I will give more specific guidance next time. As you're actually working on it though, because each thing has to generate, it's just going to be a lot faster if you work on these different techniques in a separate RMD, which is how I split it up. And you can see that if you're on Taylor and you do that symbolic link thing, I mean, you can see it actually with the files that I link out to for each of these parts on the labs. So yeah, it's going to be basically just easier for me to grade and check the work if I'm not jumping between labs. And so I would say while you're developing the labs, do it separately. And then when you're ready to submit your assignment, then go ahead and knit the whole thing. And I think actually if the way that we'll turn in the labs, if we can all get on Taylor, then I'll just ask you to share the path to in a Google form to where that file is on Taylor. And then that way I can run it and make sure it works. And then if you get stuck, also comment. So yeah. Let's see. Oh, thank you. Yeah, online or no, not. So yeah, that's a big one. And it's kind of a weird, it just would be so confusing to have mixed with some people in person and some people remote. I don't want to go there. So we're going to continue to be remote, unfortunately. If everybody could guarantee that they would be in person, I would say, yeah, maybe, but we live in now the moment of Omicron. And so if you like feel funky, then it'll be split, or or you might just feel legitimately uncomfortable coming in person because it is so highly contagious and pretty much everybody's getting it. So let's stick with remote, play it safe, and also be consistent. And I will be posting the videos and yeah. So I don't know if you have any other suggestions about how we should navigate this. I'm all ears, but that seems to be the most legit way of doing this. Okay, is this a form of unsupervised learning? Good question. Okay, so this is supervised learning. And why is it supervised learning? Because we have a response term that we're feeding into the model fitting process. So that's why it's supervised. Yeah, so I think actually I'll do a final outline before we have our midterm that shows sort of the hierarchy of what's supervised and unsupervised. But it basically supervises just if part of your model fitting involves the response that you're looking at for, then it's supervised. if you don't have that response, if you don't know what the cluster is already that you're grouping on, or you don't know what the axes are that you're collapsing with ordination. It's basically clustering and ordination are the unsupervised. And we'll get to those after this when we go into like looking at communities. Let's see. And this book is free to access, which is so cool. And all the code to generate all the figures is in there too. Yeah, this book is awesome. Yep. So these links actually go directly to the chapters. And here's the training and test data. So there's a lot of permutations with this stuff. And I'm being a little choosy with giving you guys the biggest picture overview. And this dives into a lot more detail. Yeah. Okay. So then this is what I showed before about model splitting and fitting, evaluating, predicting. And then I collapsed it in our last model when we were doing logistic regression, where basically we're just taking all the data, fitting it, and then predicting it on all that same data, just as like a first step. You will do the splitting of the actual input data into a training data set and a test data set. And then we'll use the test data set on Wednesday to do evaluations and performance. But there's another aspect. This is another book. It's a lot of the code is online, but not very good, to be honest. It's a little buggy. But the book has some good conceptual notions of species distribution models. And these guys are like some of the original, the OGs. And beyond the evaluation, what I like about this figure is that there's calibration, that the calibration is the part that says which predictor terms do we use on the X, and then how do we, it's before we do the final evaluation, and it's about all the fine tuning of the model fits. And that plays into looking at especially these trees, which you want to prune at a certain depth. The thing is that most of these techniques have a lot of these calibrations that are internal to it that you can change with arguments in input, and the defaults are generally pretty good. So you might have where that would fit in this little diagram would be like, well, maybe after you fit it, you might evaluate that model and then maybe remove some predictors or change some input arguments, like what some thresholds and cutoffs for tree depth and stuff is. So I see another question. What is the response term we are feeding in the model that makes it supervised? Okay, thank you. It is the Y. And in this overview graphic, and in your data, it is the column called present that says each row, is each row a 0 or a 1? That is your Y. So that is what you are trying to fit. And so when I do the Y tilde X, that tilde is saying in a R model formula, it's saying that Y is dependent on X. So which X's are you going to use? And then Y is the present. So when we feed these models in that model fit, we give it that present, which is just a column in a table. And that's why we had this present. And remember, the shortcut to give all other columns in your data frame is just the dot. But here with the GAM, we actually are explicitly saying for each of these, give it a smooth term. So allow this term to wiggle. if I didn't wrap this, this predictor X of altitude from the world climb, then it would just fit it as a linear model. It wouldn't give it a wiggle. So yeah, the point is that this is the Y. This is what we are predicting based on our X's. And that's on the right-hand side of the tilde. So that's the general form of this. Y is the response and X is the predictor. Now, another terminology that's good to know is that X is, especially when we get into deep learning, it's also called a feature. And so there's all this, there's a whole vast set of literature about feature engineering and transforming and getting all your inputs so that you can do a better job of predicting your response, whatever that is, whether it's like, you know, some internet cat or a puma or whatever. So yeah, hopefully that's really clear. Now, Maxent was an oddball because we didn't feed it a formula. It's trying to do a lot of stuff for you. So internally, it has its own kind of formula that it is fitting. And there are ways of constraining how it fits each term. So you can tell it how much to allow. And the other thing is that each time you add, let's say, a wiggle, or there's some extra little parameter that is part of that fitted model, then that is that's adding to the complexity of your model, of your fitted model. And you could imagine that if you have 100 points of data and you have 99 parameters, you could perfectly fit your data every time. So that's part of this model calibration and evaluation too, is understanding, well, what is the most parsimonious model? So that's where this model calibration comes in, and sometimes it's also called model validation, model selection, or variable selection. And what we want to do is we want to avoid, well, one, predictors that are autocorrelated. So that's that multi-collinearity issue that we had talked about before and you guys had last quarter. And then also variables that are uninformative and unnecessary parameters. So how it gets there. So first off, the ones that are autocorrelated, there is a general rule for Spearman's correlation. So we did that GG ally. So a grammar for graphics like ggplot has GG ally package, and then we use the GG pairs plot, and it actually gave us a correlation coefficient for each combination of input predictor. And if it's greater than 0.7, either in the positive or negative direction, then you generally want to try to figure out which of those two you want to keep in the model and not introduce this collinearity issue. So we'll get into this next time about how to actually do that. There's some packages that help you do that. And then there's also this Akaike information criteria. And this gets at this like parsimony. So parsimony just means like the simplest is the preferred. And every time we have an extra term that adds some wiggle or adds a new branch in the tree or what have you, that's an extra parameter. And we want to reduce those numbers of parameters. So we have the simplest model explaining the most variance. And so there's a trade-off between explaining the variance in your all the differences between how your predictors influence your response and how that and getting it right, and versus having too many parameters in your fitted model. And this is the most common way of doing it. And there are other little flavors of it, like Bayesian information criteria, deviance information criteria, but this is the basic idea. And this is like one of the most cited papers in the history of science. It's like, yeah, the 73rd most cited paper, because it's just in such common use. And yeah, and there's just generally parameter tuning. So we're not going to go deep into this space. It's more that you know about this, and then I'm going to probably ask some questions about, like, you know, when in next time for the overall lab, to just try to tweak a few of these things. And this is just from this chapter 11. There's with random forest, for instance, you can have a whole bunch of trees, but what you notice is that this is, so random forest, this is one of these input parameters that allows it to explain a lot more variance, the more splitting of the tree it can do. And then it tapers off at some point. So you wouldn't want to unnecessarily introduce extra parameters, extra trees, if you don't have to. And it basically applies that threshold by default for you, but you can also get in the weeds with figuring out what the best spot is. And then I just want to share a few other little slides about, like, some of the conceptual stuff that was in this habitat suitability and distribution models. So a little bit more on the environmental and ecology side. And this is just another visualization that where, let's say we've got these different predictors of water, light, temperature on each of these axes. And then you could imagine that there's some sweet spot for some critter that wants to, likes, you know, like Goldilocks style, doesn't want it, you know, too hot, too cold, just right, you know, metabolically, and etc. So that's the fundamental niche of what is preferred by the given species. And then the realized niche is where that's somehow constrained by competition and other biotic predator-prey kind of interactions. So that's the reality of it not living in a resource competition-free environment. This is another sort of interesting one that just highlights how there's like exotic climates that, so you can imagine that this is applicable to invasive species where maybe there was some original niche that you could constrain by continents, and then, you know, the like Asian bark beetle then made its way into North America and has a new niche. Or you could also imagine that these niches are also changing as a function of climate change. Things are moving. So we're having poleward advance of a lot of species, and we're having, you know, as things warm, maybe they're going higher up in elevation, and they're going maybe increasingly towards the poles as a general trend, but it's always more complicated than that if you look at all the data. Okay, and then just as a reminder of, you know, how that fits, we've got maybe these X's are where you've seen the species, and the red dots are where you have not, are true or maybe pseudo absence or just background values. All these are similar terms. And then you're trying to fit that response that differentiates between, fit a model that differentiates between those two responses, and that's its realized niche. And then you can use that model fit to not only predict where you had data before, but over the entire landscape. And so now you can put it back on the map. Okay, so that's basically it there. Yep. Okay. And so the lab is the species tree. I also, if you were using old URLs, I renamed it to lab 1 A and B to prefix that, and now this one is C. And so we're gonna, you guys are gonna actually have that response term is now going, you're gonna apply it as a factor. And that means that it's a categorical value, not a numeric value that could vary from 0 to 1, but it's telling R like, hey, I'm a factor, and that will change the distribution. In this case, a Bernoulli distribution is what's used. It's like an odds ratio where it's either a 0 or 1. It's like flipping a coin, and and that's going to be the default distribution that the underlying modeling term uses when it sees that your response term is a binary factor. It will be like, oh, I can use Bernoulli. And then you're going to use this rpart package, and it has a model fitting function called rpart. And then the ranger, actually it's that's a different package, sorry. It's called just ranger. And so these are some knitting options here to turn off the warnings and messages. And then here we're loading these packages. I'm trying to like point out here that this has to do with the predictors, the X's, and then this has to do with the data, sampling the data and splitting the training and testing data. Skimmer is just another package that it provides this nice little pretty and simple summarization of your data set. So we see that here's our response term that is a factor. We don't have any missing data there. And there's only 2. And here are the counts of my data. And then here's a histogram, so you can get a little idea of the distribution of these input variables. And here's the mean. And then we're setting the seed so that it'll reproduce the same results when you use random elements, like ggplot theme. We're getting that data again. And here we're saying ID is just to do some bookkeeping if we have some weird points, or you wanted to remove a point that was in the middle of the ocean or something like that. And then, so we're not actually going to use that to fit the model, is ID. That's just the number of the row. And then here, this is the important part, is that we use a factor, and then we omit those rows that don't, where we have any NAs. Yeah, and the set seed, there was it came up in the Slack, and it just, fundamentally with statistics, there's a lot of sampling of distributions, and there's, it's actually really hard computationally to do random number generation. And so under the hood, there's actually, it is kind of deterministic. You can get the same result from a use of a function that uses randomization if you do this thing called set.seed. Now, the number that you put in here doesn't matter. If you wanted to produce the same sample, let's say you have 100 rows of data, and you wanted to sample those 100 rows like we're doing to get 80 of those rows, 80% as our training data set, you could say sample 1 through 100, and then you have the row index. Well, if you set the seed, if you ran that again, normally in R, you would get a different result each time you ran that sample. But if you set the seed and you ran that function, you would get the same result. And so this is just a way of using randomized functions that have some random component, but then you get the reproducible result each time. that should get the same rows back. And so it just makes it a lot easier to like debug and figure out what's what. So setting the seed is just in 42, that's just, it's the answer to life, the universe, and everything from Douglas Adams, Hitchhiker's Guide to the Galaxy. And they basically used machine learning in some future society to like figure out the answer to life, the universe, and everything. So they built this monster computer, and said like, give us the answer, and the computer spit back the result 42. And then everybody's like, well, what does that mean? And he's like, well, you didn't phrase your question right. So get back to me in another 1,000 years. Anyway, so it's some nerdy things. So now the skim, we get this little nice result. And then here we use this R sample and we split this, and the strata is saying, give us based on the input data, give us a relatively equivalent number of zeros and ones as the original input. So that's a strata, and a stratified design in surveys. And anyway, strata is just like a block of information, and we're keeping that the same. So then we get our training data set from that, and then we can show like, here's the original ratio of zeros and ones with the table function. It just says how it does a count for each unique value. And so we have 499 zeros, 487 ones, and then we can do a table on what are the number present in our training data set, and it's a similar ratio, which is the point. So now we have our training and our test data set, and let's just do a really simple tree here. So we can use this R part, and here we have a formula again, and now we've got these extra model parameters. So the max tree depth we can say is 1, and so that's just going to give us 1 branching, and it looks like latitude explains the most variance, and if it is less than 7.7 degrees latitude, then it's probably going to be, there's a good chance it's absent, and if it's greater, then it's going to be present. So that's a really simple decision tree. And then we can let the defaults rip for it to then fit a fuller tree, and then prune that tree. And this is the textual description of that tree that recursively partitions. And then here we can look at, you see these are the end nodes. And so this node has a certain probability of being that, or it explains that much of the data, I should say. And you see that the amount of explanation of that data tapers off quickly with the number of the size of the tree. So that's a single tree. And then here we've got, we'll get into this more with cross-validation. That's another concept about understanding model evaluation. And this is not that interesting of a figure. But it kind of goes back to that notion that we're talking about with, we want to reduce the complexity of the model while maximizing the explanation of the variance or the increase of the accuracy. And then there's this other little package that can take that model after it does a bunch of these cross validations, which basically just like pulls some of the data out and then refits the model and figures out how well it does. And then there's this variable importance per estimation that it can look at. And we see that latitude and longitude are actually the explain the most. And if we wanted to plot some of these, we could do that. These are like the term plots we showed last time with the logistic regression. But in this case, you can see that there are the breaks of that decision tree that gives you that response. It's not like a nice smooth wiggle like a generalized additive model. Term plots are are based on breakpoints. And then with random forest, the idea is that it's actually an ensemble method, meaning that it's trees of trees that get used. And maybe I was looking for a figure that did a better job of showing that, but I'll find that for Wednesday. But we can look at this and just basically ranger here is we're feeding that data, and then we can look at how much the root mean square error is, which is not that great. And then this is based on these two different values of impurity versus permutation. So basically, it's just saying how important it is with a couple of different terms here. And I think that is explained what the difference between impurity and permutation is. I think that has to do with I don't know, actually. I have to look at that. But this is the amount of explanation that each of these variables, the ones with the most importance, are that have the greatest weight, and are basically earlier branchings in that tree. So I'm going to let you guys go for it. I'm going to make sure if you email me if you don't have access to Taylor, and then I'll kick around until the top of the hour. And I have a meeting, unfortunately, at 11, but let me put, I'm going to put a link in the chat to my Zoom, my personal Zoom place, if I can find out how to get there. And oh, great. I'll take some questions yet too. Okay. Should we consider tweaking variables if they are not contributing that much to the prediction? Yeah, so we'll get into that next time with more dropping the variables. But that is the right idea, is that if they're not very important, and especially if they're autocorrelated with other terms, then yeah, you can drop them. So you can drop them if you have the present tilde dot notation. You can just drop the column in the input data that you feed it, or you can be explicit in the present tilde dot and list out all the terms there. Is it convention to use 80% of the data to train? Yeah, so yeah, sometimes 80, sometimes 70. It's not a hard and fast rule. It does tend to vary. I have seen, yeah, even up to like 90% if it's a very rare species. If you don't have much data, there's a certain, depending on how big the range is, you need at least a few data points, and sometimes you don't have much. So there's been a bunch of studies that try to evaluate how many data points you need for the different methods and the different range sizes. And that might have to do with where you, how you do the split. And also now I'm seeing, okay, Peter's watching a video saying purity was essentially the weighted percentage of response terms that were incorrectly categorized. Yeah, that sounds legit. We can always look at these things in the help itself. So, which is the place to go, the authoritative place to go. So if I open this up and look at, okay, let's look at Ranger. Actually, I should start using my session. So if I look at Ranger, that library. Oh, that one came later. Yep. So let me look at it here. So yeah, variable importance is the Gini index for classification and variance of the response for regression. So this is where the Gini index is for like having a factor, that Y response term, and then the regression would be if it's a continuous response term. And then, yeah. So this would require a bit more of a Google impurity versus sorry, I should have known this before, just using the code, which I took from that. I adapted from that hands-on machine learning with R. And then, yeah, this is what happens when we're coding and looking up stuff is we end up on Stack Overflow. And variable importance. I'll look into this to get an answer Wednesday. Yeah, the Zoom link. Here we go. Copy invitation. Nope, I guess it's not copied. Copied. Paste. There we go. I'll send you guys an invite in Google Calendar to this same to Tuesday, to tomorrow at this time. And yeah, and yes, some of the stuff is kind of confusing. So yeah, any videos you guys want to share, I'd love to see some too. I have a little, maybe I'll make a channel. I've been keeping some, but some of the videos are like 9 hours long because they're like entire courses. So yeah, anything that's short and sweet and to the point would be great. Okay, well, I'm gonna, unless there's other questions, feel free to shout out any questions for that might interest others. Otherwise, I'll hop onto this this Zoom space and work with you individually. Okay, see you.